Alright, welcome back to Meteorology 101. We are kicking off part 2 of atmospheric physics. So in the first part, we studied atmospheric variables, atmospheric scales, atmospheric pressure, and we also discussed force, mass times acceleration. Pressure is force over area, and we discussed standard atmospheric pressure, which is 2.992 inches of mercury, or 1,013.2 millibars. So for every 1,000 feet, that one pressure decreases for height is about a 1 inch change in pressure. So this is important for aircraft as they're flying through the atmosphere. As the pressure changes, their altimeter changes, and that reflects their height, because the height is corrected for sea level, and they want to know exactly where they are according to sea level, so they can determine where they are above the ground. So every 1,000 feet is a 1 inch change in pressure, and 1 millibar equals 0.03 inches of mercury. So if you want to convert millibars to inches of mercury, there's 0.303 inches of mercury is 1 millibar. Gravity is constant at 9.8 millimeters per second, or approximately 32 feet per second. So that speed never changes. That is the gravity on the density of the atmosphere, how much mass, pressure down on the surface, and that is what gives you your pressure. It's your force over area. So first you determine force by how much mass you have times the acceleration. Your acceleration is gravity, and pressure equals how much that force over an area. Once you calculate that, then you can determine your pressures. Now, I discussed in the last video also that by the time you calculate any of this stuff, we have weather charts. It's already calculated, done for you. So if you want to do it as a hobby or for fun, that's fine. But by the time you figure it all out, it's already done. The pressure's already changed, and your numbers pretty much mean nothing. So as a weather balloon is let loose, data is sent back: wind direction, speed, pressure, temperature, dew points. So we use a SCOOT chart that is plotted by a computer, and then we can determine what is happening in the upper atmosphere and what kind of weather we can get from that. And there are so many calculations on the SCOOT chart that are done for you that you can determine how high your clouds are going to be, what your flight level winds are. If you have an inversion present and you have fog on the surface, you can determine about what time that inversion is going to break and when the fog is going to dissipate. So there's a lot you can do with a SCOOT. Your stability indices, severe weather. We'll cover the SCOOT later. That's going to be a whole separate video. What I'd like to do is just go over the parameters of a SCOOT and see just to get you familiar with that, and then we'll eventually do another video on analyzing a SCOOT. So, like I said, the computers do it for you, but it's kind of fun to do that yourself. Analyze a SCOOT based off in basically coded data. When you download the data, it's just a bunch of numbers, and you have to decode that as you plot the SCOOT, and then you can actually calculate your own indices for stability, see your inversions, and temperatures, winds, and it just gets pretty fun to see what you can do with a SCOOT chart. So atmospheric physics part 2. Alright, depicting what pressure on weather charts. So like I said, by the time you calculate anything, it's already done for you. And on the surface chart, we are looking at the isobars, constant lines of equal pressure. So pressure is depicted on charts in basically two ways: constant height and constant pressure. So on a surface chart, you're going to have lines of equal pressure. On the upper air charts, the 850, 700, 500 millibar, 300 millibar, you got constant heights. So as it takes the pressure at those heights, then the heights on the 300 millibar level, then those are lines of constant height, and you can see where your troughs and ridges are and what kind of upper level support you have for the surface system. So constant height surfaces, the height everywhere on the chart is the same. It's called the surface analysis chart. So that's a constant height surface. Now, these are all corrected for sea level. Measured surface pressures at locations above or below sea level are corrected for sea level using estimation of the atmospheric conditions. So, like I said, these are corrected for sea levels, and that's mainly for aircraft. So, after the chart is plotted, these are computer generated fronts. We have low pressure centers, which are honestly wrong most of the time from the computer data. That computer data will extrapolate these lines to make them more smooth, and then the high pressure centers and low pressure centers sometimes are off centered just a little bit. So you have to kind of analyze these charts yourself to determine exactly where your centers are. Plus your fronts, as you go through with wind direction, speed, temperatures, dew points, you can determine exactly where your fronts are. And like I said, these computers just throw in a bunch of fronts, sometimes just extrapolating data. So it's all computer generated. So as you look at these charts, you just reanalyze the data for yourself, looking at the surface plots, and then determine what's correct, what isn't, and you can make small corrections in your forecast for your area. So the surface chart, the pattern of the pressure variation on the surface chart is depicted connecting like pressure values with lines of equal pressure called isobars. So we just covered that, and then those spacing of those isobars are every 4 millibars on surface chart, and then they'll mark your low and high pressure centers. And then the red dashed lines are isotherms, and they are lines of equal temperature. And when they cross those isobars, you can see where you have thermal advection, and that will indicate if that's going to affect the temperature at your station. If you have warm air advection, then you need to correct for that and forecast your temperature a little bit higher. Cold air advection a little bit lower. Plus, warm air advection going into a low pressure system. If it's winds rotate counterclockwise around the low and into a low, so if you have warm air advection on one side of the low and it's going into the low, then that gives you less mass with the warm air advection. Warm air rises, and then that will deepen that low. So that low will intensify based on that information. So you can learn a lot, just see a lot from these surface charts. And then once you get closed low systems, rotation, frontal systems, then you can see the depths of that low. And if it comes to an occluded low or just a full low pressure system with a triple point, or the frontal systems coming out of that low, you can go to the upper levels. Like I said, see major shortwave troughs. You can see another closed low stacked toward the colder air in the upper levels, and that shows that you have upper level support for that low. And is that pressure system in its developing stage, a mature stage, or a dissipating stage? So then you can look at the fronts, see how the fronts stack back on the upper levels, and you can tell, are they just supported by a major shortwave trough, a minor shortwave, or are they supported by an upper front? And you can see the slope of the front, and how as that cold air approaches the warm air in the warm sector, then is it going to, if that front has a steep slope, is it going to plow that warm air, moist air, or is it going to have a shallow slope and then just kind of slowly pick that up and then have all the weather at and behind the front? So active cold fronts, inactive cold fronts, how fast they're moving, what the slope is. You can determine all this from surface and upper air charts. So we'll get into some of that stuff a little bit later. I do have videos that explain a lot of that. Go back and look at those, but right now we're looking at just explaining what the surface charts are. We're kind of starting back from the beginning. I did a lot of videos just kind of explaining how we use these charts, how we analyze these charts, and Now it's just trying to get back to the basics and explaining how do they come up with these charts. So every hour, these stations put out METARs, which is a weather observation transmitted over the internet every hour, and this data is plotted across the United States. And then the computers can analyze that data for pressure, temperatures, dew points, cloud cover. Pretty much, there's so much to a surface analysis that to a surface plot, it all depends on how much information that observer wants to put on that METAR. So then the computer can analyze these and determine where the low pressure centers are on the surface, and then lines of equal pressure, temperature, and even dew points. So you can analyze pretty much whatever you want with these charts, and then go to the upper levels, which is every 12 hours, at 12Z and 0Z, the National Weather Service, most of your stations, National Weather Service stations, will launch a balloon, weather balloon, and that sends back the data with the winds, temperatures, dew points, pressures in the upper atmosphere. And there are mandatory levels, like I said before, was the 850 millibar, 700, 500, 300, and then they will go all the way up to 200, 250, 200 millibars, and 100 millibars. So up to 40, 50, 60,000 feet, depending on how far that balloon makes it before the balloon pops and then the radio sound hits the ground. But they'll send back that data. The computer collects that data and then plots the upper air data. And then at these mandatory levels, when we do these charts, we'll do the 850, 700, 500, 300. Typically, I do the 250 and 200, just depending on what time of year, to get a better picture of the jet stream, because these basically do a cross section into the jet stream. It's basically a horizontal cross section into the jet stream, and as you go up on the next level, you can see if the jet maxes are reaching up there, and try to get a picture of that jet stream as a whole. All right, 1,500 millibar thickness. This is basically once you hit 1,000 millibars, which is approximately 364 feet off the ground, 111 meters, you reach your area where there is no friction, so it's not affecting the winds, not slowing the winds, backing the winds. So when you get to the 1,000 millibar layer, and they take the heights all the way to the 500 millibar level, you can kind of get a picture of where, how thick the atmosphere is from 1,000 to 500 millibars, or from 364 feet to 18,289 feet. That's the area that this chart predicts or shows. It's not really a prediction, it's an actual data, and you can see where your heights are. So with the high pressure centers, from the 1,000 millibar, basically the surface data, and then the 500 millibars of the red dash lines on this one shows your heights at 500 millibars. You can see if I have a low pressure system on the surface, do I have rigid in the upper levels. So if the low pressure is very intense on the surface, it's pushing that mass up, up vertically, then it could hit the tropopause at the top of the troposphere, and then just start building pressure, and you can actually have a high pressure upper level high. Low pressure or high pressure on the surface, you can have so much mass dropping down in that high pressure, have a massive high pressure system on the surface, and then the mass on the surface, the mass on the upper levels really can't keep up with how much mass is hitting the surface, so it actually creates a lower pressure in the upper levels, and you have an upper level low. Once that happens, if you get thermal advection, moisture advection in the upper levels with an upper level low over a high pressure system, then you can get precipitation in the upper levels that fall through the high pressure system, and depending on how cold that air mass is, if it's below freezing at 600 feet, 1,200 feet, your freezing levels, then you can determine what type of precipitation that you're going to have. So it can actually, all the precipitation is created in the upper levels, falls through the dry, cold air mass on the surface, and then freezes before it hits the ground and becomes snow. So you got to look at the height of that high pressure system, the temperatures of that high pressure system, and then how intense is the low pressure system in the upper levels. You have shortwave troughs going around the lows. Is there a major shortwave associated with that low? Is it a closed low pressure system in the upper levels? Is there significant moisture advection that's going to create the precipitation to fall through that high? Because everybody thinks high pressure. Hey, look at the surface chart. I got high pressure on the surface. We're clearing 7. Not necessarily. If you have an upper level low, major shortwave trough, creating the instability, the lift in the upper levels, then you can get the precipitation to fall through the high. And then, like I said, the freezing levels are going to determine what your precip type is on the surface. I do have an article on that. You can go to meteorology101.com and just type a search in for precipitation types, and it actually gives you a definition of the precipitation types and also a complete article on freezing levels and how to determine what type of precipitation hits the ground based on freezing levels. So the upper air charts, contour lines connect points of equal height, like a topographic map. Heights are expressed in decameters. Standard interval depends upon the level analyzed. So, like 300 millibar charts every 120 meters, 60 meters on a 500 millibar chart, and every 30 meters, 700 to 850 millibar charts. That's the spacing between the lines. Like on the surface was every 4 millibars. So, these are every 30 meters of height is depicted on the 700, 850 millibar chart. 60 meters, 20 meters, depending on just changing your, as you change the height through the atmosphere at those levels, how far apart those lines are going to be. So the 500 millibar chart, for example, like I said, is right there at 60 meters. So every 60 meters you're showing, it's hard for me to read that, it's on a small screen, 54, 60, 55, 20. So every 40 meters. I guess it was every 60 meters. Let me read this thing again. So that should be 54, 60, 55, 20. Okay, 60 meters. 55, 20 to 55, 80 to 60 meters. So every 60 meters that changes. Now you can see where these contours get tight. That's a tight gradient right there, and even with the isotherm, so you're going to have a lot faster winds in this area. Now these isotherms temperature change over distance. These are running parallel with these contours, so it's really not any major thermal advection in that area. So that's why you pretty much don't see moisture. You don't see anything. There's a high pressure system on the surface. What we've seen was on the that surface chart was older, and this one, the high pressure system over Alabama, there's on the surface. So pretty much got clear skies, and this shows clear skies pretty much all the way up to the upper levels also. But with the 500 millibar chart, it says every 60 meters change on the heights, and then those are depicted based on these upper air plots from the National Weather Service. So here are your heights: 300 millibar, 500, 700, 850, and 1,000. Those are pretty much your standard heights, the mandatory heights that are reported. Now I'm showing that in meters and then also in feet. So like I said, the last video I talked about everything being in the metric system. Well, there's pretty much cloud height on a surface. METAR is reported in feet. The SCUT charts, you're pretty much going to look at feet, and then anybody talks about 300 millibar charts, about 30,000 feet. So 300 millibars, it's just easier to remember 30,000 feet instead of 9,100 meters. So 30,000 feet in the atmosphere. 250, you get up higher to like 33, right at 34,000 feet, and then 200 millibar, but 38,662 feet. So you can use whatever numbers you want. You go on the metric system or standard, but you talk about cloud heights. If you see that on a METAR or surface observation, that is going to be in feet. If it's 5,000 feet, then it's 050 is how it's depicted. Few, scattered, overcast, broken. 050, that tells you where that cloud height is, 5,000 feet, and how much of it. Scattered, few, scattered, broken, or overcast. Broken's a ceiling, considered a ceiling, and then obviously overcast is. Bies-Ballott's law. With the wind to your back, low pressure is going to be to your left, and that is in the northern hemisphere. So that's usually determine wind direction using contours, isobars. You just stand outside, you put the wind to your back, you know the low pressure's to your left. So if the low pressure's to the west or southwest in the United States, then and you're in Arkansas or Illinois, then typically the weather moves from west to east, and a lot of low pressure systems will move from southwest to northeast. So if you put the wind to your back, you know if in the next few days, day or two, whatever, that low pressure system is approaching you, and you could have adverse weather. Features on the constant height pressure charts. These are pressure charts. Basically, the surface of low center is a point at which the pressure height is minimum. The high pressure point is where the pressure height is maximum. So, like I said, these are computer generated, so they kind of determine based on the station plots where that high or low center is going to be. So if you look at the elongated areas out of a high pressure system or low pressure system, then you can see where the troughs are. So kind of just looking at this one, the way these elongated areas, like the troughing out of a low or a ridge out of the high, you can look at these wind directions. The wind's out of the northwest, and then they begin to shift that to the out of the southwest. Then you can actually take this based on these temperatures, dew points, wind directions, and see where that front is coming out of the low. The frontal system drops down below these wind shifts, right between those, and then since the wind's out of the southwest there, we can bring that front back. So bring it back into the, typically they'll sit right in the trough. Sometimes the trough, you can have a prefrontal trough, which is, that trough will be ahead of the front, so then your front will be back here. Or you can have a postfrontal trough where you can bring the front is actually out here, and then you have a trough behind the front. So you got to keep an eye on that too. You got to look at those. You can still have the wind shift with the trough, but then you're looking at temperatures and dew points to determine exactly where that front is. And like I said, that front can come out of that low and be well ahead of that trough. But typically, the low pressure system sits right in that trough. As deep as this trough is right here, this low pressure system having a closed isobar around it, and then another closed isobar around it, that would kind of indicate that's a pretty deep low, and would likely be an occluded low. So it's wrapped around itself pretty good. The cold air pushing in, lifting the warm air, and then you'd have a cold occlusion. With the occluded low, the occluded front would actually come into the cold front and then back into the trough. If you have a warm occlusion, it's pretty much where the warm air is pushing up, and it's pushing up over the cold and moving faster than that cold and catching up with it, pushing back over the cold air. Then you have a warm occlusion. You can take occluded front out of the low and then stretch it right into the warm front, so it would look more like a T. And then your cold front would come out from that triple point, depending on how far your occlusion is, and then bring that cold front back into the trough. So that's just another tool to use to determine if you have an occlusion, where the moisture is, to get the wraparound moisture. You can have this moisture just wrap all the way around that low because it's so intense, it's just wrapping itself up with the moisture, and then it's well into its mature stage at that point. So you can actually get snowfall back behind this, wrapped around that low, and then pushing up over the cold air that's behind that front, and then causing more precipitation behind that low and behind that front that wouldn't normally be expected. So just another feature to look for. Gradients. Gradients is just a change of some quantity over distance perpendicular to the isopleth. An isopleth is just a generic term. That's the lines of constant anything. So if somebody says isopleth, it's just like line of equal temperature, line of equal pressure. So the effects of the contour, say pressure gradient, if lines of equal pressure, and the gradient, if you have a tight or loose gradient. So if you have a tight gradient on lines of equal pressure, pressure gradient is what initiates the winds. So the tighter the pressure gradient, the stronger the wind speed. The tighter the thermal gradient really doesn't matter unless you got thermal advection. So if you got the contours, lines of equal pressure, perpendicular to the thermal isotherms, and then you got warm air advection, then that tight gradient matters. Now that tight temperature gradient, you can use that to indicate placement of the jet stream. Once you get, the jet stream is basically caused by the north-south temperature gradient. So once you get into the upper levels of the north-south temperature gradient, how tight that is, those tighter areas are going to be where you can actually locate the jet stream. So you can do that from that 1,500 millibar thickness chart, or anything above 500 millibars. Get up to 400 millibars if you have the data to actually plot that, or 300 millibars is the most common, and then depending on summer and winter months, what the level of that jet stream is, based on heights of the atmosphere because of the seasons, and then 250 millibar, 200 millibar, you can actually see the tighter thermal gradients, and then placement of the jet stream. Plus 100 millibar, if you go up that high, up to 40,000 feet, then the jet stream can get that high to polar front jet. So you got to pull. Like I said, I always pull most of them charts to get that horizontal picture of the jet stream, and then pull the charts even above that and try to get the whole picture of the jet. So temperature, degree of hotness or coldness measured with a thermometer, and degrees using some definite scale. So the scales: Fahrenheit, Celsius, and Kelvin, the three most common scales we use. And you'll see Celsius on the METAR plots. On the surface chart will actually show Fahrenheit, and then the upper level charts will actually show Celsius. We don't use Kelvin unless you get into the scientific factors of temperature, and then 0 degree Kelvin is the point at which all molecular activity comes to a stop. So I don't think we've ever been down that far. I think as far as we've ever been is down in the 30s for the Kelvin scale, and I'm sure molecular activity was pretty slow at that point. All right, so temperature gradient. Temperature gradient is the rate of change of temperature per distance. So based on the isotherms, I got perpendicular to the isotherms. Temperature gradient. So you basically, perpendicular to isotherms is just over the distance is perpendicular to the isotherms. So just see what your temperature gradient is, how tight that temperature gradient is, based on how far the lines of equal temperature are apart from each other, perpendicular, just measuring perpendicular. Horizontal temperature gradient. Temperature gradient is directly proportional to the change in temperature. So that temperature gradient changes as with the temperature if temperature increases, the gradient increases. Temperature changes are normally expressed in Celsius degrees or Fahrenheit degrees, as in how many degrees of change have occurred, versus what the temperature is. So if here's somebody talking about Celsius degrees, they're talking about a change in temperature. So we had a 4 Celsius degree change in temperature. The temperature went up 4 Celsius degrees. That's a change in temperature. The actual temperature would be, it's 50 degrees Celsius or 50 degrees Fahrenheit. That would be your normal terminology. So that's the difference between Celsius degrees and degrees Celsius. The equation for temperature gradient is the delta symbol that represents change in temperature, divided by the change in distance. N represents distance. So how much temperature changed in a certain distance, you can calculate that. Like I said, I don't get into doing the equations because the computers do it for you. The data is pretty accurate, and by the time you calculate that time is long gone, and you can already determine what happened by looking at a chart. And you can download that data every hour, and you can analyze that data yourself. So you can actually go on ads, aviation weather, or weather.gov, and pull up ADDS. It's show all the METARs, actual latest METARs that were plotted. You can print one of those, and you can actually sit there and analyze that chart if you want. So the isotherm gradient example, like I said, measuring perpendicular to the isotherms, lines of equal temperature. You measure that distance, what's the change of temperature over distance, and you get your thermal gradient. So a loose or weak gradient indicates temperature change is small. The isotherms are widely spread. So the way they spread more up here than they do here, and that's a tight thermal gradient. That's a loose thermal gradient. Lapse rates. Lapse rates are very important for severe weather. The vertical temperature gradient, the rate of change of temperature with height. Symbol is the Greek letter gamma. So basically, if you look at the change in temperature equals the upper temperature minus the lower temperature. So how far, where the temperature decreased, following a SCU-T chart, it's all plotted, how high the upper temperature, what the temperature is at that upper part of the inversion or the upper part of the gradient line where the temperature decreased. To get to the end of that, what's that temperature minus the temperature at the lower part of that inversion or that temperature decrease, and then you got your answer for the horizontal thermal gradient. So the main thing on this is standard US lapse rate is 6.5 degrees Celsius. So your lapse rate, how much change in temperature with height? So 6.5 degrees Celsius degrees to change. We're talking about change of Celsius degrees per kilometer. That is your standard atmospheric rate. Now the change in temperature. Now if you go higher than that, then you're decreasing a lot faster. You have a steep lapse rate. Get up to the 7 to 8 mark, then you can actually have severe weather at that location. So that's the main thing, is to look at the lapse rates. The steeper the lapse rate, the more potential for the instability of the atmosphere at that location to produce severe weather based on, other parameters, temperatures, dew points, what's your moisture advection into the area, instability, low pressure, high pressure, what do you got for, stability in that area. So when the temperature does not change with height, it's called isothermal. So it's just a straight line up to SCU-T, no change in temperature. And the parameters found on SCU-T can be used for forecasting clouds, precipitation, atmospheric stability, moisture content. We talk about that, turbulence, icing, severe weather. So use the temperature, go up to SCU-T, follow a dry adiabatic line, run across the dew point, and what height you would expect clouds to form at, say, a convective, based on convection, just daytime heating. The heating heats the surface of the earth, the heat rises and brings the moisture to a certain level to where condensation occurs. That this SCU-T chart can tell you what level that is. The lifting condensation level, the LCL, that is, say if a front came through or if the winds were perpendicular to a mountain range, you have some mechanical lift that lifts the moisture, frontal system, mountain range, whatever, lifts the moisture. What level, if that air parcel was lifted, what level it would have to be lifted to become condensated and create clouds. So there's, like I said, there's a lot of stuff you can get off the SCU-T chart. And then, like I said, instability, winds, turbulence. Turbulence, you're going to look at the wind bar on the side. And, depending on what the wind speed is or direction, that mainly the wind speed, if you go up the chart and the wind speed start changing, certain certain speed per 1,000 feet or per say from the 850 to the 700, what's the change in wind speed per height to determine if you have moderate, severe, light, whatever turbulence. And then you can see the rotation of the winds too, if the winds are veering or backing with height, and then that can determine what kind of rotation you have at that station, and also determine the stability. So there's a lot you can do with all the winds on that SCU-T chart also. It's going to be a little while before we get to the SCOOT chart. I'm starting back, like I said, from the beginning with Physics 1. We're on the second video right now for Physics. I think I have 5 total. So as we get through these, and then we get into atmospheric dynamics and stuff like that, then we'll start maybe even in Physics 2, the second part. I'm going to have Physics 1, Physics 2, atmospheric dynamics 1, 2, and 3. So we're going to be here for a while. And we'll get into the SCOOT, I think, pretty early on, but I may just do a video in between these classes as far as analyzing a SCOOT, showing how to decode the data. That would just be like a hobby, fun video to do, just to show you guys how it works. Alright, so the lapse rates we talked about. So isothermal, no change in height with temperature and height. So that's just one that's isothermal. We got, okay, from the surface, typically in a standard atmosphere, temperature decreases with height. How fast that happens, how much it changes with height. Say here's 2 kilometers, then we changed, it's about 18 degrees, 17.5 degrees. Say 17. That's almost 14 degrees per 2,000 feet. So you're looking at 7 degrees per alright, I'm going to call this standard. So I don't know why they do that. Okay, so with the lapse rate, like we said, with no temperature change with height, it's called isothermal. I already wrote that on there. Like we said, with no temperature change with height, it's called isothermal. I already wrote that on there. When the temperature decreases with height, that is a positive lapse rate. That is normal atmospheric change with height. As you go up in the atmosphere, it gets colder. That's normal. When you have an inversion, you have a negative lapse rate. Temperature increases with height. Now you have an inversion. Now, when you get up to the base of the inversion is, say, 2 kilometers, the height of that inversion is 3 kilometers. So you have a pretty thick inversion there. The only way to break an inversion is to increase the surface temperature, or increase the temperature at that height, or decrease the surface temperature. So you can bring it down. Then you got a total, let's see, so the only way to break these inversions would be cool the upper air temperature, bring it down, and then that would continue with that lapse rate. Now it's no longer an inversion. Or increase the base of the inversion temperature to bust that inversion, or you could decrease the temperature on the surface. That would actually be probably more of an inversion, but it'd be a higher inversion, so your temperatures are more uniform, through the upper area. So you decrease that temperature, you can pop that inversion. So the significance of an inversion is typically if you have warm, moist air on the surface. So the only way to break these inversions would be cool the upper air temperature, bring it down, and then that would continue with that lapse rate. Now it's no longer an inversion. Or increase the base of the inversion temperature to bust that inversion, or you could decrease the temperature on the surface. That would actually be probably more of an inversion, but it'd be a higher inversion, so your temperatures are more uniform, through the upper area. So you decrease that temperature, you can pop that inversion. So the significance of an inversion is typically if you have warm, moist air on the surface, overnight cooling drops the temperature at the surface. So overnight cooling, you get an area in the atmosphere that the atmosphere starts to cool, and then it creates that increase in temperature with height. Then that inversion will actually be a stable layer, because we live in a part of the atmosphere where we are unstable. So temperature decreases with height. You have cold air over warm air. That is an unstable environment. Cold air wants to sink, warm air wants to rise. So you want to, it automatically is unstable and wants to have mixing. So when you start increasing with temperature with height, then that is a stable layer because the warm air wants to rise, continue to rise, and that cold air wants to continue to sink. So it's not fighting against each other. It's a stable environment. When you put a stable layer above an unstable layer and you have mixing with the proper moisture, low winds, you can't have many winds, you know, anything less than 6 knots, just enough to stir up that moisture, create some mixing at the surface, cap it off with a stable layer, then you can get some pretty significant fog at the surface. That's the main thing on an inversion. Another thing with the inversion is when you get the stable layer, radio waves can go up, hit that inversion, and come back. If you can get, if you have warm, moist advection underneath this inversion, like down in the south or southwest, like Texas area, you can actually, you'll have that advection pumping warm, moist air in at the surface below this inversion, this cap, and that cap is just holding everything down. So as soon as this temperature increases, this temperature decreases, the inversion breaks, then all that warm, moist air that's been pumped into that lower levels will just explode and can just shoot up and become a severe thunderstorm within minutes. I mean, it's like, it's a loaded gun is the terminology for that, and it just warm, moist air at the surface, capped by an inversion, their inversion breaks and it fires, and you can just have those cells just pop up so fast that next thing you know, you got severe weather in that area. So it's just something to look at for the lapse rate. This is just a chart showing temperature, just showing these inversions. Temperature could decrease with height and stuff, but like it's kind of similar to a SCOOT, but there's a lot of other lines on a SCOOT: moist adiabatic lines, dry adiabatic, temperature, dew point. You can actually see where when you plot these things, you use those lines to plot your temperatures and dew points. You have two lines. You have a temperature, and then on the other end you have a dew point, which the dew point's always lower than the temperature, and then you can interact with those two together and plot different areas on that SCOOT chart based on those moist adiabatic lines, dry adiabatic, then determine your stability indices, stuff like that. So this isn't a complete SCOOT chart. This is just kind of showing how that's plotted. So if you have the temperature at that height, the next reported temperature, and then you just connect the dots. And then you have your temperature line, and you can actually see what's going on in the upper levels. Same thing with the dew point. And then once you get within like a 5-degree dew point depression, which is difference within a 5-degree or less difference in temperature and dew point, if your dew point reading was right here, then you could say, okay, we have significant moisture at that level. And then you can say 2 kilometers, they're most likely going to be clouds. So it's something else to look for on that SCOOT chart. And then this just gives you an idea of what it looks like after it's plotted. So we'll get deeper into that later. So where I'm at, 44 minutes. Let's see, I want to go, all right, we'll get deeper in that in a little bit. I do want to go hit the charts real quick. So let me get you over. Let me get to the right screen. Okay, so I have a program. It's called Digital Atmosphere, and I can download data, all the surface plots, upper level plots from SCOOTs, so we can actually analyze these charts. So we're going to look at surface for now. Actually, a fun thing to do is just kind of look at the let's go look at the satellite. Let me get you over there. Okay, so let me get my pen over here. I'm going to draw on this thing a little bit. Alright, so as far as the satellite, I see a lot of buildup right there. That is kind of lee side of the mountains. I'm going to look at, see what's going on there on the surface. So if I'm looking at something, these features here, I'm going to start looking at this, and then follow that up. I see some ridging here. Looks like cirrus pouring over the ridge. Follow that and look for some rotation. So, do we see any? I see this pushing north. See some higher clouds pushing from the southwest. I'm almost putting that low, pretty close right here. Frontal system, cold front, and then my warm front. So low, front. Alright. Great Lakes region, what do we got going on here? I'd say we have, let's see, definitely that low pressure system well to the north. And then probably an occlusion and a low coming out, or a cold front coming out of that. But let's look at this. We got high pressure, definitely in the south. Alright, so let's go. I'll keep erasing that, but we're gonna go pick some blue for high. See that a little bit better. Like I said, low pressure well to the north. Try to stay politically correct here, I guess. A low. Maybe you have a little bit of a frontal system there, a troughing coming out of that low. Did see what's going on there. Like I said, the low pressure there. Warm front. Let's see, sitting there talking about low pressure. Cold front, warm front, low pressure. Maybe a cold front there. High pressure definitely there. And then I would say rotation. This is just a, looks like subtropical jet. Rotation, and then winds out of the south, pushing this moisture up, and then that's causing most of this. So a little bit of troughing through here, maybe to give that lift it needs. Look at the clouds just dissipating out here. So we're dry over in central Texas. So give you an idea what kind of where the dry line is. We just have moist advection from the south, wrapping around this high. Warm sector, winds out of the southwest. Probably winds pushing out of the northwest there behind that front. We'll have to check that out. And then maybe another frontal system there, but we got let's see, jet stream. Then that probably breaks off somewhere, but we could probably put our jet right through there, and then the subtropical jet to the south. Alright, so Great Lakes region, a lot of moisture off the lakes, pushing on shore. Got that rotation, wrap around moisture right there on that low. Warm sector, pushing warm moist air to the north. Alright, that's a mess, but that's just a general idea, just looking at satellite. What do we have? Alright, so let's go back to our chart. Get my mouse going here. I can't see anything. Okay. Low pressure in the panhandles, Texas, Oklahoma. Low pressure over in Nevada. High pressure in the south. high pressure up northeast of the Great Lakes, and then probably some low pressure to the north of that. Let's get our isotherms on here. We're going to use Celsius, and just always do, because it's less cluttered on this program. Surface temperatures, and then we'll just go over here to get this plotted. Come on, things running slow. Actually, let me go close out a couple programs so we can speed this up a little bit. Alright, there's our isotherms. Tight thermal gradient over the plains, even to the southeast. So that would typically show, if it's that far, low pressure in the panhandles, Texas, Oklahoma, low pressure over in Nevada, high pressure in the south, high pressure up northeast of the Great Lakes, and then probably some low pressure to the north of that. Let's get our isotherms on here. We're going to use Celsius, and just always do, because it's less cluttered on this program. Surface temperatures, and then we'll just go over here to get this plotted. Come on, things running slow. Actually, let me go close out a couple programs so we can speed this up a little bit. Alright, there's our isotherms. Tight thermal gradient over the plains, even to the southeast. So that would typically show, if it's that far south, I mean, get an idea about your, like I said, with that we've seen on satellite, that subtropical jet. There's station plots on here. I got 85% of the plots. If I go 100% of the plots across the United States on this whole chart, it would just be black, red, blue. You won't be able to read anything. So these get pretty cluttered at 85 to 87%. So we're going to just do that for now. Alright. So we'll go with our pin. Let's go. Fog. I'm going to have to go. You're not going to be able to see my drawings again. Get out of here. Alright. Get rid of this. Alright, get you on that one now. Okay, so now we got the surface plot, surface chart up. I can start with that red was fog. Mist. It's like the fog or mist. We gotta see what the visibility is. So visibility is just to the left. That's like 5 miles visibility, 10 miles. See, there's 5 miles visibility. That is mist right there. We got 6 miles visibility right there. So we're just running mist right now. It's a little later in the day, so just running mist. Maybe in that high pressure center could have been fog. So our visibility is probably dropped because the high pressure creates that. The surface plot, surface chart up. I can start with that red was fog. Mist. It's like the fog or mist. We gotta see what the visibility is. So visibility is just to the left. That's like 5 miles visibility, 10 miles. See, there's 5 miles visibility. That is mist right there. We got 6 miles visibility right there. So we're just running mist right now. It's a little later in the day, so just running mist. Maybe in that high pressure center could have been fog. So our visibility is probably dropped because the high pressure creates that inversion, holds that moisture to the surface, and then becomes a pretty significant moisture at the surface and well, reduce visibility. So got the low pressure here. If we look at winds, our wind shift, we go over here, and cold front, we got a wind shift here. So that would actually almost be no thermal advection, so you'd almost just be, that'd be a stationary front coming through here, wrapping around that high a little bit. But if the high pressure is moving to the south east, could be an area of a cold front. But with the wind shifts the way they are, completely perpendicular to each other in direction, one going this way, one going this way, here's your shift right there. I'll put a front. Man, that'll be tough to put that. I'll put the front there for sure, but I'd say, you know, with the way these wind directions are just starting to come out of that area, there's no real major thermal advection. You know, you got your isobars, you got your lines of equal temperature, your isotherms, but there's really no isobars crossing here. So if this trough dropped down and gave me another isobar, I'd say, okay, we got thermal advection. But that's not the case, so I would bring the cold front down to here because there's rotation around that low, and then bring stationary front out. Now the high pressure system, we know winds are clockwise around the high, so now we got winds out of the south and pushing that warm, moist air up into Texas and Arkansas. So get rid of that. And okay, what do we say over here to the, well, to the north, maybe a low, kind of shifting here. That's a warm front to me, with the winds out of the southwest and winds shooting out of the east, southeast. So that's a, yeah, let me get it back in here. That, I would say, definitely the warm, definitely that warm sector right in here. Now we said that low to the north, and then did we have any winds out of the north? I was looking maybe to have some winds out of the northwest, but I'm really not seeing that. I'm seeing out of the south. These are the mountain range too, so these winds, they're very light, 5 to 10 knots. I mean, that mountain range can shift those around. There's a 5 knot. I mean, but here's, we can pretty much determine with this low pressure system. All right, overcast, broken, overcast. So we're pretty much moisture all through here. So we got significant moisture all the way through there. Looks like some fog to the north. There's some rain. So with the low pressure system, there's the wind blowing that way, this way, this way. We do have rotation right there. If we said that cold front, let's see, the warm front was there. We brought that cold front down. These wind directions don't agree with that, but let's go 42 to 06. So there's a cold, that's a cold temperature there. It's a warm temperature there. Let's see, make sure I'm right on that. So that 06, 42, no, that's a, that would be like 46. So 42, 46, 38, 51. There's a jump. Probably bringing that cold front back, and then becoming stationary because there's no isobars to cross these isotherms. So bring the front back into a stationary front. So it's not the right colors. Warm air, cold air. So stationary front back into that area. So mountain range, lift, moisture, onshore flow. Really the winds are going that way offshore, so that ain't really helping us. Try to see where, you know, it just pretty much just be mechanical lift, winds pushing against the mountains, all in this upper elevation, and then causing all that moisture, you know, condensation. So depending on how old this data is too, sometimes this program doesn't upload the latest stuff. So broken in Columbus, scattered in Indiana, overcast in Illinois. Got a lot of moisture through here, a lot of moisture through St. Louis area and Missouri there, the whole state of Missouri. All right, so I'm trying to get this, working with this pen. Doesn't exactly work every time you tap the screen. So alright, a lot of moisture we said from the south. Frontal system. Let's go put the frontal systems on this chart just to see what the computer says and find out where we are we were saying a front here, maybe a front here, warm front there, and then find out what's going on over here. We got a low pressure system. That definitely looks like a little bit of rotation. So warm air advection. There's your warm sector here. So maybe just a inverted trough out that low. The computer system is probably going to put a frontal system there. Let's see, 74, 73, 62. So you'd almost go right through there. 62 and 74, you'd have to have almost like a cold front, but your winds are not really jiving with that. 63 to 75. 64 to 61 on the dew points. 58, 28. Let's see, 30s. Dew points on the 30s, 60s. So it looks like if you had a dry line, it'd be way back here. You're not that dry line we were looking at. That's just maybe just a that frontal system out of that low. That's what the colder air, 75 to 63. That's just that area of colder air not allowing the moisture. So we did see that drier portion right in the center of Texas. So that wasn't the dry line. That's an actual frontal system. So let's see what this chart says. Let's go. Alright. We got an occlusion out of the low pressure system to the north. I'd take that low, put it up here, which they do have a low further north. Push that, be an occluded low, coming into a warm front, which we did call that, and then back out of that cold front, back out of that off the triple point, back into across that isobar right there, and then become more stationary. So they're actually putting another low and then warm air advection to the north of that. So depending on your wind directions, I mean, you got winds out of the southwest. I don't see anything. There could be some plots in here because we're not 100%, but pointing some winds out of the southeast to bring that warm air advection around that low. Calm winds behind it. Here's your north westerly winds pushing down onto the cold front, so cold air advection. But I would say that's pretty weak too. I mean, with this isobar, I mean, where's the other isobar to really give you that offshore flow here? Alright, we got an occlusion out of the low pressure system to the north. I'd take that low, put it up here, which they do have a low further north. Push that, be an occluded low, coming into a warm front, which we did call that, and then back out of that cold front, back out of that off the triple point, back into across that isobar right there, and then become more stationary. So they're actually putting another low and then warm air advection to the north of that. So depending on your wind directions, I mean, you got winds out of the southwest. I don't see anything. There could be some plots in here because we're not 100%, but pointing some winds out of the southeast to bring that warm air advection around that low. Calm winds behind it. Here's your north westerly winds pushing down onto the cold front, so cold air advection. But I would say that's pretty weak too. I mean, with this isobar, I mean, where's the other isobar to really give you that offshore flow here? You know, you got moisture, but I don't see a heck of a lot of support for that cold front. So we did say low pressure off the coast, and then maybe bringing that cold front down and into a stationary front. I mean, that could wrap around that high back up and into this low pressure system. Could just have a stationary front coming through, and then I wouldn't say that either because you have way too much warm air advection. So I'd put a lot of warm. I would almost bring that warm front out of that low across, and with the winds out of the south being warm air advection, that's your warm sector. So I would disagree with this chart. And then the high pressure system, we did see a lot of clearing to the south, and then a lot of moisture north of that. So with the frontal system, like I said, bring that warm front across out of that trough, and then with that's your lift, and then mainly a stable environment with moisture, so you do have your clouds there. So then you have your subtropical jet, that was way down here, and then your regular jet. Let's go see the polar jet, where that ends up and supports all these fronts, because you can't have a jet stream just shooting straight across a bunch of fronts. You're going to have some support there too. So let's go after a 300 millibar chart. put the jet maxes on here first with the colors. See basically where the center of our jet is. And then we'll go after pressure. That's approximately 30,000 feet. So we can see the jet maxes. We got winds out of the north, winds out of the up in the northwest United States, and we got that jet finger off the over the Atlantic. So let's go pressure. This is the lines of equal height for 300 millibars. And temperature. We're going to go with that. All right. Station plots. We need to do those too. I'm going to go basically 100% on those plots because the upper level data isn't cluttered like the surface because of the balloons. There's only so many stations across the United States that launch on balloons, so you get a lot less data than you do on the surface. Many more stations that report hourly observations than there are that actually launch balloons and have the equipment to do the upper air soundings. Okay, so winds out of the southwest, pushing up, coming back down. There's a jet max, 100 knots, 90 knots, pushing back to the south, and then we got convergence here with the subtropical jet. 70 knots, 65 to 70 knots there, and then we go up to, I'm showing a 60 knot wind right there. Go over just a hair. No other plots. That's just a buoy. Well, I'd say a buoy, but there's got to be that's actually Bermuda, I guess, that launches that balloon. So subtropical jet merging with the polar front jet, convergence in the upper levels, and suppression of moisture and everything at the surface. So you got, that's all the way to the surface. You're pretty much no clouds, no moisture here. We do have some moisture over St. Louis, and that's where we're seeing that low pressure on the surface that was pushing out warm air. We had the warm front out of that low, pushing the warm air to the north, had that warm air advection, and we was possibly seeing that little bit of a cold front over central Texas. So this is basically ridging in the upper levels. We don't have, support for that low. I mean, you have, unless it's pumping out so much mass, it's creating a ridge in the upper levels. But you basically, your jet stream is, the thermal gradient and your contours, that's our ridging right there. The isotherms aren't crossing a whole lot in this area. I mean, they're crossing there and then dropping right back down, so there's no major thermal advection in the upper level. We do have moisture over Nebraska, Wyoming. So here over that mountain range where we had all that moisture, a little bit of rain, definitely that's an upper level trough with thermal advection, so you can see that. Let's go crossing here. Maybe you're not even seeing that either. Let's go right around here. Let's see. Alright, I'm not even on the screen for you to see where I'm pointing. Alright, let's go back to display and let's draw on this thing. Okay, so let's keep that on there. Red, weak thermal advection right there, upper levels. There's all our moisture. So no matter what we got on the surface, we had the moisture in the upper levels. We had the moisture on the surface, but basically they're reported on the surface because we have this trough that supported that low that was on the surface, and then we had that cold front. So we got a trough in the back, supporting that. So here's a wind shift here, troughing, and then instability with moisture and a jet max pushing into that let's keep that on there. Red, weak thermal advection right there. Upper levels. There's all our moisture. So no matter what we got on the surface, we had the moisture in the upper levels. We had the moisture on the surface, but basically the reported on the surface, because we have this trough that supported that low that was on the surface, and then we had that cold front. So we got a trough in the back, supporting that. So here's a wind shift here, troughing, and then instability with moisture and a jet max pushing into that behind that low. So here's another jet max, winds coming down, then we have subtropical jet, and then emergence with the polar front jet. We had that warm air advection from the south with that low pressure system. We got ridging in the upper levels behind that. Still got some moisture. Still got moisture all in the northeast. That was another low pressure system that was off the coast. We had low pressure well to the north, cold front. Let's go clear this out a little bit. We got that trough. Really no thermal advection. There might be a little bit right there pushing that air south, but there's, as far as, there's a trough, troughing. We got the upper level trough. It's not really a major short wave, but it's, it's a pretty good sized trough that gives that low pressure that was on the surface the upper level support. So that's good there. And then the low that was over Arkansas area, what do we got there? We had that frontal system kind of over central Texas we were looking at. Kind of support we have for that. There's a trough. No thermal advection though. Nothing significant. That's a ridge, and then this thing had that front and the back, but that we didn't agree with that front too much on the surface because we just didn't have the support for it. So, but with this, let's see, thermal advection right there. These are parallel. This one comes down. It went parallel. There's really nothing there. You got your little bit of thermal advection right there. Now we don't have the major warm air support for that lower warm front, but we got, still got the troughing, still have the upper level trough for support for that, and the jet max pushing through, and then the long wave ridge, and then we got the jet max over western Illinois. So all right. That's pretty much it. We can go later on. This video is getting pretty long, so we're gonna go surface. Get out of there. 850, 700, 500. We can go through all the charts. I've done that on other videos. You can check them out. I mean, we'll do it again. I'm gonna go through, keep going through the charts as I do these videos. Try to apply what we're learning with the thermal advection, isotherms, lines of equal temperature, lines of equal pressure, lines of equal height, iso plus, that's just the generic term for everything, and then start pushing, applying that physics data to the charts, and then you can start seeing the picture of what's happening from the surface to the upper levels, depicting on the details in your area, so you can see, okay, if I have a dew point, say 65 or higher on the surface, and a cold front is approaching, I probably want to be prepared for severe weather. Stuff. That's pretty much it. We can go later on. This video is getting pretty long, so we're gonna go surface. Get out of there. 850, 700, 500. We can go through all the charts. I've done that on other videos. You can check them out. I mean, we'll do it again. I'm going to go through, keep going through the charts as I do these videos. Try to apply what we're learning with the thermal advection, isotherms, lines of equal temperature, lines of equal pressure, lines of equal height, iso plus, that's just the generic term for everything, and then start pushing, applying that physics data to the charts, and then you can start seeing the picture of what's happening from the surface to the upper levels, depicting on the details in your area, so you can see, okay, if I have a dew point, say 65 or higher on the surface, and a cold front is approaching, I probably want to be prepared for severe weather. Stuff like that. So I want to say thanks for watching. If you don't mind, share the video, help me get some more viewers. I need some more subscribers on YouTube. Get to the point where I need to be monetized, and just, I know it's ads and stuff like that, but um, appreciate anybody that's watching, and thank you for watching and your support. We'll see you next time. And thank you for watching and your support. We'll see you next time.